All right, thank you. It's a pleasure to be here. So yeah, so I'm going to talk about this project that's joint with Abigail Ward, and kind of the goal of the project is to understand homological mirror symmetry for Looijenga pairs in a particularly like in a tropical geometric, as much of a geometric way as possible. So, and from a particular view of point of view on the Fukaya category that I'm going to try to explain. So, okay, so but let's first, I'm not going to assume that people know what these are, so I'm going to start with the definition. So, definition. Okay, so a Looijenga pair so it's a pair YD. So maybe I should write an English sentence. So is a pair where Y is a smooth rational surface in the algebra geometric sense, is a four-dimensional real manifold. And D is a singular nodal divisor on Y in the anticanonical class. Well, when I say, okay, so it's, I'm going to make a remark in a second, but since the surface, I'm just saying that it's nodal, it's going to be normal crossing. So in particular, even more than that, so no, because we're working this particular dimension, this implies that D is either just a cycle of P1s, or it's just a one P1 with the two nodes glued together. So or it just looks like. Okay, so in particular, it is simple normal crossings, but because this is kind of the because of the dimension, and U, which is Y, the complement of D and Y, is a log Calabi-Yau. So meaning that there exists a holomorphic volume form omega on Y with poles with simple poles along D. Okay, that's not going to be so important for this talk, but I am going to say some things about the complement U. So at least keep that notation in mind. Yeah.
So is the assumption of divisor class the thing that's controlling the topology here? This is like
that and the fact that like Y is rational. Yeah. Okay. So and I'm going to also, I mean, you'll also see where this comes from, because I'm going to give you like a general recipe how to construct any of these things. Okay, so maybe just start with some examples. Okay, so the first, the ones that I understand the best and like a lot are the simplest, are just like toric pairs, where Y is just some toric surface, any toric surface, and D is a toric boundary. For example, maybe something like P2 and 3 lines in P2.
Can you give one?
Yeah, that's not gonna. Yeah. That's not the only example. Examples is this is the first in the list, so I'll give more examples. Oh, another toric surface. Okay, I mean, another toric surface may be like a Hirzebruch surface. So, I mean, another one that you might not be super happy with is P1 cross P1, but or a Hirzebruch surface where here I have something like the divisors. I'll label it so there's 4 P1s in the boundary, and the intersection numbers are like 0, 0, n, and minus n. Okay. I just mean that that it's birational to P2. So for instance, like of course all toric things, once you remove D, then you just have C star squared. Okay, so some non-toric examples. Well, maybe not. One step that you can do, which maybe not so exciting, is you can take Y to be toric and D to be a non-toric anticanonical, which from the point of view of mirror symmetry still does something kind of non-trivial. So for example, maybe I take P1 cross P1, and I instead of taking the 4 lines in infinity, I smooth one of the corners. Okay, and then there are operations that you can do on these to get one from more of them. Get more of them from one. So right. So these are not okay. So they're like the S1 action. I mean, it's not invariant under like there's no C star action. It's not a equivariant divisor. Yeah. Yeah, there's a C star squared action on this. On the toric boundary pieces, there's an induced C star action because it's 1 dimension lower. Well, I mean, it's trivial in one direction. Okay. And then you can also, what you can do is start with some YD and perform blowups in D. Okay, so I'm going to explain what I mean by that. There are 2 types of things that you can do. So one, you can do what I'll call an interior blowup. Which looks like this. So you have some piece of your chain of P1s, and you take some point inside of this some dk, and you blow up there, and you get some new variety with some exceptional locus E, which is hanging off here. And here I have dk tilde, which is in the class, the pullback of dk minus E. Okay, I always forget the sign, it's minus. Yeah. Yes. And I said D, so this is what's called the proper transform of dk. In this example, the proper transform of all the other divisors which don't touch this point are just going to be the pullbacks of themselves. And I take and then the divisor, which is just the sum over these proper transforms, is still anticanonical. Okay, or the other thing you can do is do a corner blow up, where you blow up one of these corners, which has a little bit of a different flavor. No, I just choose some components. I take their blowups, and there's a map. I take the proper transform of all the divisors under that birational map. And I mean, some of them where I didn't do blowup, all I'm doing is pulling them back. But if I did a bunch of blowups in each one, then I take them with whatever happened. Okay, and then the picture for this, of course, is I have something going on in my cycle of curves, and I blow up at this point. So here I have dk and maybe dk plus 1. And both of these are now going to get some exception. So I'm going to add the exceptional locus to my collection. So now I have E here. Here I have dk plus 1 tilde, and here I have dk tilde. And each of these now are in the class the pullback minus E. And we can take an anticanonical divisor, which is the one that I drew, and d tilde is equal to E plus the sum over I d I tilde, the proper transform. So you see, this is still, so when you do a blowup, the anticanonical changes by a factor of minus E. In this case, you pick it up because the only thing that happens here is a minus E to the divisor that you blow up in the interior of. And here, you pick up 2 minus E's from each of these, and then you add another E here. Okay? So,
You don't want to fill up the weight of the divisor because that gives you a disconnect.
right, I don't want to blow up, I mean, right, I want to keep a connected divisor. I don't want to blow up something away from that. I want to have this cycle of curves at infinity that is my divisor. Yeah. Okay, so now let me just say what's known about mirror symmetry for these pairs, and then I'll explain it and our perspective on it maybe. Okay, so the kind of starting point that really gets you going if you want to try to understand mirror symmetry for these pairs is the work of Gross, Hacking, and Kiel. So Gross, Hacking, Kiel. So what they do is produce from this chosen, when you work in this pair, you use the pair, but they produce a mirror which I'll call U check to U using SYZ and Gross-Siebert principles. So they don't actually construct like some kind of special Lagrangian torus vibration, but I mean, there has been some recent work doing that in some cases, but more of from an algebrogeometric perspective, they can construct this U-check. And the hard part in what they're doing is really because they're thinking about mirror symmetry not in the direction that I want to discuss here, but so the hard part of their paper is constructing U-check algebraically. So what I'm going to explain to you is the easy part, where, or I mean, the part that I'm going to need as input is the easy part, where I only care about U-check as a symplectic manifold, which is which you'll see doesn't require. So in order to construct U-check algebraically, you need to do something like count holomorphic disks, which is a lot harder problem than what I'm going to show you is just draw some picture and tell you how to construct a symplectic manifold. Okay, and more recently, Hacking and Keating have studied homological mirror symmetry for the pair. So what they've done is for a distinguished, so these unlike the toric ones, these Looijenga pairs in general have moduli of complex structures on them. But for a distinguished complex structure, on YD, they construct a Lefschetz vibration W from this mirror to U, so to C, which somehow records a divisor at infinity for mirror symmetry purposes, and proved homological mirror symmetry. That the derived category, at least for this particular complex structure of Y, is equivalent to the Fukaya-Seidel category of this vibration. Okay, and in particular, they do it in a way such that the fiber of this vibration is identified with the divisor D, and it also allows you to delete the divisor and get homological mirror symmetry for this open thing. And there have also been some recent results that maybe are not as relevant for the talk, at least, that doing mirror symmetry for the open part without the divisor using microlocal sheaf methods. But I'm not going to say too much about that. Anyway, so now you might wonder, okay, so at least for some case, this homological mirror symmetry is already understood. So what's our goal? Is to understand this HMS equivalence more generally, in the sense that I mean that I don't need to restrict to this distinguished complex structure, and in a way that's more in line with Gross-Siebert. And maybe also like has, so in general, like this Lefschetz construction, it really depends on the fact that you're in this particular dimension. And if I have some more general framework that's kind of more going through tropical geometry or something, you might hope to also apply it to like higher dimensional log Calabi-Yau pairs. Okay, so let me state, and we can't, so far we can't actually do this full equivalence, so their result is much stronger, but let me state what we can do, and then I'll kind of explain how it works and maybe what one can, how one can improve on it. Okay, so let me state a theorem. Okay, so given any YD, there is a well-defined okay, so I'm going to say some words that I'm going to hopefully define later, or at least explain later. Monomally admissible Fukaya category which has a collection of objects sorry, I should say, let's say of Lagrangian sections of some torus vibration, whose objects are in bijection with the Picard group of Y. So the group of line bundle, they're in bijection with line bundles on Y. And moreover, if you take a Lagrangian that is mirror to something ample and supported on D, then, okay, and I guess I need one more. And L0 corresponds to the structure sheet. Then Hom of L0 with L. Okay, so this is some kind of like homogeneous coordinate ring of Y, because I'm looking at like maps into some ample line bundle and I can take its powers. Matches. Yeah, L is a Lagrangian, sorry. It's an object of the Fukaya category. I should have maybe been a little bit clearer. Does that make more sense? Then the Hom is concentrated in degree 0. and has a basis corresponding, consisting of, I guess, of integral points of some polytope. I guess it's not really a polytope. I should say of an integral affine polytope. Let me write P sub z of z. So the integral points inside of this polytope, where what is this polytope? Where P sub z is a polytope studied by Mandel. Let me just write it this way. The integral points of this polytope also index sections of O of z. And that part is due to Mandel. Okay, so what this says is if you give me any pair YD, I can produce to you some kind of Fukaya category on Lagrangians, and you check that I'll explain kind of at least morally what it is. And yeah. So I'll consider only the objects which are sections, which should be mirrored to line bundles. And those objects are in correspondence with line bundles, and you can compute some of their homology, at least the first order. So this is only as a vector space. And the point is that this construction is like very geometric, maybe. And then, okay, so maybe that's all I'll say for now. And then I'll try to explain how this works. Right. Yeah. I mean, so only the. Sorry. Let me. Yeah. So maybe I did a poor job phrasing this particular sentence clearly. It should say. Let's say this is corresponding to OZ for an ample divisor Z supported on D. And when I say it's supported on D, I mean that Z can be written as a sum of the components of D. So so for the toric pairs, that's true for every line bundle in a toric variety can be written is generated by the toric boundary divisors. But for a general pair, that's not true. If you start doing a bunch of blowups, you can have some divisors that sit in the interior and have zero intersection number with the boundary, and therefore cannot be supported there. Yes, I think so. But what I'm saying is just that, okay, I mean, you might want to know, I mean, even if I can do it just for D, you might also want to know that I can do it for more divisors, right? I mean, this is a restrictive condition on D. It's not that, like, you cannot find such a thing for any YD. Right. I mean, okay, I mean, I don't know if I'm going to have enough time to actually get to this, but maybe I'll just say it now. You would hope, like, so this is one direction of going about mirror symmetry once you start with this moreover, where you kind of explicitly try to compute the Homs between the Lagrangians. But like by like indexing their intersection points and then trying to compute their mu k's. I mean, I think that that's not the correct way to do it in general. I mean, that's nice because you can kind of try. So what you can do is now you have these points and you can try and like count some tropical curves that correspond to morphisms. But what you would like in general is to have some kind of statement where you do some kind of like Fukaya-O argument and just reduce everything so you can just compute with arbitrary line bundles. So, and if you're familiar with like the toric case in general, like this way of doing it is like what Muhammad does in his first paper on toric mirror symmetry. And then what you would really like is to do like the analog of the second paper, but it's a little bit unclear how to do that in the presence of singular fibers of the SYZ fibration. Yeah, so okay, so that I will try to explain. Well, okay, let me just, so the L0, suppose that you're first in the toric case where U check is just C star to the N, then L0 is just the real positive locus. Or if you think about it in terms of like the SYZ fibration comes from like taking the cotangent bundle of the base and then quotienting out by a lattice, L0 is just the zero section of the cotangent bundle, the image of that under that. So, but that's kind of not a canonical. I mean, that kind of comes from some choice. You could always choose, like when you do mirror symmetry, often you want to take a choice of section of your SYZ fibration, and you just call that the one that corresponds to OY, because you could always just twist everything back. So that, I mean, like twisting by a line bundle is the autoequivalence of the derived category. So you could always take your homological mirror symmetry functor, twist, and then have a new like homological mirror symmetry functor that defines different, that identifies the. Yeah. So there's, in some sense, if you think about the base, you have some like nice like semi-canonical choice of like the real positive locus or the zero section or something like that.
I guess there's a better symmetries of the SYZ vibration.
Right. I mean, once you start doing more blowups, there are less symmetries. Okay, so let me try to explain a little bit how this story goes, because it's kind of very nice and geometric. So, all right, so where am I? Over there. Okay, so no, I mean, there's a paper by Mandel that proves that. Yeah. It's like his thesis, I think. Because I mean, because these sections are like theta functions in the mirror, it's not super obvious. I mean, in the toric case, it's like the classical thing where you just draw the polytope of the toric variety with that ample divisor, and then which corresponds to some symplectic form, and then count the integral points. But here it's a little bit different because it's not actually a polytope in like flat R2. It's like a polytope with some integral affine structure. Okay, so how does this work? So the thing that really gets you going in constructing this, like the space where the Lagrangians live, at least, is the following proposition. So which is in GHK. So suppose that YD is any pair. Then you have a diagram. Then there exists a toric pair. Y bar, D bar, and a diagram it looks like the following. So I'll think that I start with my pair YD, then I do something, get some other pair Y tilde D tilde, map this pi1. These are all birational morphism. And here's my toric pair here. And this is such that this pi2 is a sequence of interior blowups. And pi1 here is a sequence of corner blowups or blow downs, depending on what your perspective. I mean, if you think that you start with YD, what you do is a sequence of corner blowups, then do some interior blow downs, or if you think of the other way, then vice versa. Okay, so let me do one example of this. Yeah. These pairs are closely related to cluster variety. I don't remember the precise state, but yeah, yes. I mean, all the sorry, in this dimension, the complement, like this log Calabi-Yau, is always a cluster. So somehow, I mean, so this subject is also very closely, you could also try to frame it in that perspective. I would like to frame it more in the perspective of general mirror symmetry for pairs, but this is saying that there's something very special about this dimension, because it's not true in general that you could like take some toric thing and birationally relate it to your thing by such a sequence. Okay, so let's do some example. Oh, just that there is always such a diagram. So they're particular, those particular transformations that I wrote before. So if I start with a toric pair, you can think about it in the following way. If I want to think about how to get all possible YDs, I can always start with a toric one. I know very much about them because I can just draw some fan in R2 or whatever. And then I can do a bunch of interior blowups on the toric divisors. And then I can blow down whichever -1 boundary divisor I have if I want to. And what this is saying is that every single pair can be obtained from that procedure. Yeah. So for example, maybe I take the pair, which is P1 cross P1, which has this smooth corner. And well, okay, so I'm gonna label them by their intersection numbers, self-intersection numbers. So this curve has self-intersection 2, and these two still 0 because they're line classes in P1 cross P1. And okay, what I can do is I can blow up at this corner, and I'll get some other pair, which, if you think hard about it, is the blow up at 2 points of P2. And the boundary divisor obviously looks now like this. 0, -1. I have this -1 curve E. And this has self-intersection 1. And now, okay, if you think about it carefully, there's an exceptional curve that dangles off of this on the interior, and I can blow that down. So, and this I can relate to the blow up at a point of P2 with its toric divisor, which has intersection numbers like this. Okay, so you can see at least here. Okay, so you can see at least that you might not be super convinced about this because all I did was like do some blow up so that I got the right intersection number for this to be the toric boundary of the blow up at a point of P2. But it's actually also a fact that among if you look at pairs and you just think about only the cycle of P1s at infinity and their self-intersection numbers, if you write one that has the same intersection numbers as a toric one, then it has to be that one, the toric one. So in general, YD is not determined by the cycle, but toric ones are determined amongst all of them by the cycle. Okay. So what can you do with this now? So from a choice of this, so if I choose y bar d bar in one of these diagrams for my YD, GHK construct an integral affine space B, which is homeomorphic to R2 by the following recipe. And as we'll see, you should be thinking about this B as like the SYZ base from your symmetry purposes, but looked at from like a bird's eye view. So like looked at from very far away. I'll be more clear what that means in about 5 minutes. Okay, so here's the recipe, and then I'll draw an example. So so you should think about this as somehow starting here and doing something to get these. Okay, so one, you just start with the non-singular affine R2. I did it right. Sorry. You also, in addition to this, you also get a fan. So not just the base, you get some extra data. Okay, so I start with a singular non-singular affine R2, which is just the base of like some log map on the interior of the toric thing is what you should think. And the fan, and a fan sigma bar for y bar. Okay, then what you do is to add monodromy which looks like 1 plus k AB minus k a squared k b squared 1 minus k AB along any ray generated by AB, where this map pi2 does k interior blowups in the corresponding toric divisor. Okay, so that's the effect of pi2, and then the map pi1 doesn't really do anything to the base, but it changes the fan. So And then for 3, delete rays in sigma bar corresponding to divisors that are blown down. In pi 1. Okay, so let's do this particular example. I think it'll be a little bit more clear what's going on. So I'll think of it more from the perspective of starting with the toric guy. So I start with the blow up at a point of P2. So I have some kind of flat R2. And I draw the fan of this, or a fan of that. Okay, and then, yeah. Sorry, no, the fan is, in this case, the fan is still at the origin for now.
Monodromy, for instance. So the example that I'm making, monodromy, you use this transformation to Brook charts.
So this monodromy is really along that ray.
Sorry, by monodromy, you really mean like you use this transformation to Brook.
So what I mean is that if I think, so I'll think about the integral affine as a picture in R2, where I draw flat R2, and then I draw some lines in it, where if I cross that line, then the lattice in the tangent space changes by that transformation. You could unpack this into gluing some charts together that all look like cones. But for what I'm about to do next, it's better to think in terms of these base diagrams, where I actually draw an embedding away from some lines of the integral affine into R2. Okay, so now, I think this will also clarify your question. So now I do a blow up in the interior of one of the divisors that has intersection 0. So in my picture, maybe it's that one. So what I do is add singularity at the origin of this integral affine space. And I remember that there's a ray here that's parallel to this. But now I draw some dashed line here. And when I cross this dashed line, I do the transformation like this to the integral affine structure. Okay. And when I blow back down, in this case, I just forget that there was a ray here. You could imagine doing like much more exotic things, but where you just take the toric thing and do however many blowups as you want, and then whichever ones are -1 curves, you can blow them down. This is the same example. Yeah. So this is corresponding to P1 cross P1 with this. Okay, so and if you had done more blowups in the interior, now you have some kind of complicated singularity at the origin. So that's what I mean by it's like the bird's eye view of the SYZ vibration, because everything is kind of pushed to the origin. So so to get an honest base, you just push the singularities out parallel to the ray. So I mean, in this case, it would have been fine, but What do you mean? There's no monodromy unless I did an interior blowup on the divisor.
Okay, so you don't add all the other ones.
Right. So I add the monodromy, like the k degree monodromy, where k is the number of blowups that I did on that divisor. So within the star of that ray. Okay, so for example, I might think that in this example, I mean, everything's kind of okay because there's one singularity. I could just take this slit and I can just slide it anywhere that was within the star of the ray that's now missing and put it like somewhere like that. Maybe in a more complicated example, what I would do. So maybe I started with P1 cross P1 and I did like two blowups here. I did maybe one blowup here, and then that was a -1 curve, so I deleted it. Then I could push these off and separate them. So I have something like this. And how far these slits, these x's slide out. So now there's 3 singularities in here, but the monodromy around them is all just degree 1. And how far these slits go out doesn't really have any meaning, but how far they go within the star of the ray, you should think corresponds to where on the divisor I did my blowup. I mean, it does correspond to that. But okay, so now what's the point of this? So work of Symington, which like builds on work of Zhang, says that if you have any base diagram like this, then there's a unique symplectic manifold with an almost toric fibration over it. So let's call it B. The idea is that we started like 5 minutes late. Okay. Yeah. Okay. So the idea, maybe I won't write it, but the idea is that you can glue in like above each of these, you should have a nodal torus fiber. You can glue in a standard neighborhood of that to where over the rest you just take T star of the base mod the lattice. Okay, so the result of this theorem is you've produced some symplectic space just by drawing this diagram, which is the SYZ mirror to U. Okay. But that doesn't use this fan anywhere. That just uses the location of just drawing this integral affine space with some monodromy. I get such a fibration. And so then the point is, what does the fan do? Topologically, yes. Yeah. But of course, their construction, as I said, is much more complicated because you need to do some corrections to the complex structure. No, but there is an argument for it in the Hacking Keating paper. And it's not like something really complicated. So what does this fan do? Okay, well, from my perspective, what it should tell you is it tells you how to control Lagrangians at infinity. So namely, at infinity, you check looks like, or near infinity, I should say. Looks like the cotangent bundle of the base model lattice. And in the star of array, generated by alpha, you should require that theta sub u of alpha is 0, where u theta are coordinates on T star B mod lambda. And this makes sense because alpha is the monodromy invariant direction in that region. Okay, and then very briefly, I'll just say like what happens. So then what our result comes from classify sections with this property in terms of tropical data on B, which matches with which also determines a line bundle. So in the toric case, this is just like a piecewise linear function with respect to the fan. So I guess I should say on the pair B with this fan. Okay, and analyzing that gives you the objects of this category that correspond to line bundles. And maybe if somebody wants to hear the details of that or how you get this polytope, then I'll leave that to question section. Thanks.
Can you explain again how this singularity of the origin where you have all this one right object gives birth to those singularities that you can prove for that?
you just take the you take some toric thing like this, and the singularity has a particular form, right? So you just do some blowups where you know, like this, say I did 2 blowups here, like in the one that I drew, and then I did maybe 1 blowup here, and I had some ray there, but since that one's a -1, maybe I could erase that ray. So what I can do is I want to think about this. I should think about this as coming from like a bunch of, I mean, in this dimension, the only singularities really generically are just these nodal contractions. I should think about this as coming from a bunch of those where these are the homology, correspond to the homology class in the torus that's getting crushed, like these directions. And okay, well, what I can do is I'm just gonna, and all I'm gonna do is just slide them off in the direction that they came from. So if there were 2 blowups here and 1 here, all I'm gonna do is remember that points in that direction, and just draw a base where I keep this fan and I move each of them so that they're now at different spots. So and these maybe have degree 1 since there were 2 of them, and they stay within the star of this ray that was here. And here I'm just going to do the same thing with that one. And it stays in the star of this ray that was here before. And the point is that you should think that if I was toric, then how do I get to this P1 at the boundary? Well, if I want to get to the fan of it, then I take the star of that ray and I take its quotient by that. Well, therefore, the heights of these, the direction, so in Symington's theorem, where I put this x along its monodromy direction gives me the same symplectic manifold, but where I put them here does matter. So the heights of them correspond to where I blew up on the divisor. In particular, the case that Hacking Keating do is the case where all of these are still lined up with the origin, because in that case, the symplectic manifold is exact. And because the only exact torus fibers you can have to be along the monodromy direction. So therefore, to have like an exact torus fiber over the origin, you have to have them all line up. Does that answer your question?
So you are recording the Lagrangian to be fiber over the trace?
No. So what I'm going to do now, if I have some picture like this, is I have I have the star of this ray, maybe like a little bit inside of it is this big region here. And on this region, the condition, like if I look at infinity, the condition that theta 1, because this is like the ray 1, 0, if I think about this as away from the singularities at infinity, the 1, 0 direction is the monodromy invariant direction across any of these. And theta 1 equals 0 makes sense. So I'm going to require that my Lagrangian here, everywhere here satisfies this condition. And then everywhere here on some region like this, I'm going to require that theta 2 is 0. So there's going to be a big region where it's just like my 0 section at infinity, but there is some twisting that happens in the. Yeah.
And
okay, so you construct these. So these Lagrangians look like, okay, so now you need to ask, like, how do I actually get such a Lagrangian? Well, if I was in the toric case, I would say just take a PL function with respect to the fan. Here I'm going to tell you to take what's called like by Gross, which is kind of a not very complicated name, but a multi-valued a sheaf, an element of the sheaf of multi-valued integral piecewise linear functions, which just means that on each neighborhood of a singular thing and on the whole thing, I take a PL function with respect to the fan, and they differ by linear things on the overlaps. And so my Lagrangian comes as graphs of those. And then I take the Legendre transform of that, so I map by the gradient of it. And that maps me to a dual integral affine space where the polytope lives. And if my thing was ample, so that map is like 1 to 1, because it's a convex function, then the image is going to be some polytope. And the integral points actually directly correspond to the morphisms with L0.